let's start today, review dynamics for civil engineering. And as you can see from the specification, the current specification for civil, for dynamics, talk about kinematics, mass moment of inertia, force acceleration, including particle and rigid bodies, and then work energy and power for both particle and rigid body. And of course, it's 4 to 6 questions out of 110 questions. And for the reference for the FE, go to dynamics for the current version 10.01 is at start at page 118. So let me go to make a very brief about the concept of dynamics, and then we go to practice 8 problems for that one. So let me recap what we learned in dynamics, and then we can go to practice some problem that select for wide variety of topics that is explained in FE. So as you can see, just very quick here, we start with the dynamics, and of course in the dynamics we have kinematics and kinetics, right? So we have kinematics, and then we have kinetics. Just something that a few equation that I try to capture here, and then we can go into the problems. The first equation, very important, is the relative motion that apply for both particle and rigid body. And I think just try to recall what we learned, right? So if we have the two particle A and B, then in terms of the velocity and talk about the vectors, of course, you can have distance, you can have the acceleration. So you have it VA, then it equal to VB plus relative of A relative to B. And of course, similarly, we can have acceleration for point A equal to acceleration for point B, and then relative acceleration of A relative to B. There's something different, and that apply for both, rigid body and particles. And in this case, for acceleration, just something that sometimes we missing is the normal components of the acceleration when the body or the particle moving in a curvilinear motion. And of course, we also go to further in kinematics, as you see in the specification of FE review. We can have the particle. For here, we can have particle, and then we can have a rigid body, bodies. And for the kinematics, we have the 3 methods to solve. The first one is force acceleration. When have a problem at one instance and mention about acceleration. So we want to find out the force or acceleration. Then at one given instant, that we'll use the force acceleration method. When it talk about positions, from position 1, position 2, then we have a work energy. And then the last one, if we talk about the time at different instant in terms of time, then we have the impulse momentum. And work energy, impulse momentum, it tends to find out the velocity, either angular velocity or linear velocity. And of course, from both kinematic and kinetics, we have some equation that I want to just write down here. When we apply equation, hopefully it recall for you a little bit. So if we're talking about the velocity, then we can have v equal to the first derivative of distance relative to time. And then similarly, if we're talking about the acceleration, and we have two components, if it's curvilinear, so I write in a general form. So we have acceleration in tangential components, t. So it will be a second derivative with regard to time. And then in terms of the nominal component, an, for curvilinear motion, so it will be v squared over rho, which is the rho is stand for radius of curvature. Radius of curvature. And we also, when it's the body in rotational motion, then we can have relationship with the regard to the angular velocity and angular acceleration. So with that, we can have v for at given point, at any given point equal to omega. So any body, any point on the same body will have the same omega, but different point on the same body have different linear velocity v, omega r. I just make it simple like that. And then if we talk about the tangential components of the acceleration, it equal to the angular acceleration times the radius from the point we take in moment to the point for the velocity, from the point that body rotation about to the point that we take velocity or acceleration. And of course, we can also have the an components. It equal to omega square r. Omega radius the angular velocity, alpha angular acceleration. And of course, similar to the v, so we can also have the omega. We have omega angular velocity. It equal to the d theta rotational angles over dt, and we have acceleration, angular acceleration alpha, angular acceleration alpha, it equal to d omega over dt, and it also equal to the second derivative of theta dt. So those are a few equations that apply, and I want to write down, and then when we go to the problems, other information, other equation, just like what is the equation to apply for force acceleration, work energy, and impulse momentum, I'm going to write equation so that you can recall and apply it. So with that one, let's move to a few problems that I just prepare for now, and then I just analyze this and show the solution. So for this one, you have a body, so this is a rigid body, and they are not talking about the forces, just talk about the geometry of the motion. So this one is the kinematics problem, right? And the question is, if the acceleration of b is 60i minus 20j meter per second square, the acceleration at point A is most nearly. So they give you the acceleration at one point, in this case point B, and then we want to find out the acceleration at point A. Given one point properties, find another point properties. And just recall I and j. I is the unit vector along the x-axis, and j is the unit vector along the y-axis. So it always, when you have a given point properties and they ask you another point properties, always go through the body properties, whether that 2 points on the same body. If those 2 points are not on the same body, then we need to find out the common point between the two bodies that hopefully those 2 points are located on. Okay, so that the process should be. In this example, and that typical for the FE, simple problem, we have 2 points A and B on the same body. So we just only focus on that body. So with that one, they give us also the alpha, and that is angular acceleration, and omega angular velocity. Alpha is 100 radians per second square, and omega is 20 radians per second, and give us the geometry from B to A. So as you can see, I is the unit vector along the x, and for the acceleration B, we can write down is given AB vector equal to 60I minus 20J, and of course that unit is meter per second square. So 60I, so it I unit vector follow the positive x-axis 60. So you can find out that is the component here 60. Of course that is meter per second square. And then the y component is negative 20. J is positive y going up, in this case negative, so going down 20 meter per second square. And the question asks is what is the acceleration of point A. So we can unknown, and we can break it down into x and y components, find out for x and y, just like you do in the engineering mechanics that already reviewed previously. So you can have that in statics. So you have that ax, right? Ax, and we don't know the direction. We can assume it positive going up, ay. So acceleration at a in y components and in x components. Then go to the equation that I just derived earlier. We have it here. Acceleration a equal to b plus a relative to b, and now apply that, we can rewrite equation, right? So a equal to b plus a relative to b, so that the same equation that we have. But don't confuse, if we start a, then a relative to b. If we have ab, then it equal to aa plus a b relative to a. So with that, just go on to write that Rafastic that you already remember, that one, or the one that I just wrote it down here. Then you just two equations, two unknowns, because this is the 2D, right? 2D can be able to project the relative acceleration equation, aa equal to ab plus aa relative to b into x component and y components. So this one, just like we can project that in the x-axis, right, and assume positive direction. And this one is y-axis, and assume is positive direction is going up. So you have two equations from the Rafastic, the diagram on the left, and just project, we can find out. So abx already given 60, and then a over b in normal components, because that is the relative acceleration, and you can see that two components, tangential and normal components, because this is rotational, right? And previous equation I just write here, normal components equal to omega square r, and tangential components equal to alpha r. So what is the normal or tangential? Tangential is perpendicular to the radius. In this case, the radius we assume as if B were fixed and A rotate about B, because that is A relative to B all about. So, and we don't know, assume going up, and that, as you can see here, perpendicular to the radius. Normal components parallel to the radius and point to the point. In this case, we assume it as if this body rotate about B. So it point to the center B. And that, as you can see, that's why we have A relative to B normal component to the left, and then A relative to BT, tangential, and same direction of alpha. Alpha in this case is counterclockwise. Then, of course, the AA over B, tangential component go up. So with that, with the equation, normal component omega square r, we can be able to find out negative 100 meter per second square. Similarly, ABY given, and then AA relative to BT, that is tangential, equal to alpha r. Alpha is 100 radian per second square. R, the distance between B and A, 40 centimeters. So you get 0.4. You can have 20 meters per second square. And that is X and Y components. So X is I and J. So we can have that. So the answer will be B, as you can see there. Any question for that one? Let's see, any question or no? Let's continue for the next problem. Hopefully you recall a little bit. So that is the kinematics, and we learn a few concepts in here. That's why I do this. Relative motion, review of normal and tangential components of the acceleration. If you have only velocity, the question is give you velocity, then you don't have the normal component, just only the tangential component, because that is the velocity always tangent to the path. You can see that. So you don't have the relative velocity, don't have the normal component. Now move on to the next problem. And this, the previous one deal with the acceleration, and this one we discussed about the velocity. Okay, so velocity. So there are 3 bodies, link AB, BC, and CD. 3 bodies. And they have AB either linkage mechanism shown, and they have at that instant they have instantaneous counterclockwise angular velocity is 10 radian per second, just so on the finger. What is the instantaneous angular velocity? So that is omega of link BC when the link AB is horizontal as shown, and the link CD is vertical. So we have the angular velocity. This is the question asked. What is the angular velocity of BC? So that the question here is omega BC. What is omega BC? And they give us the angular velocity of link AB. So that is, we can have omega AB equal to 10 radian per second. So give us one body properties, find out another body properties. The previous problem give us one point property, find another point. This one is body to body. Make sense? So as I stated earlier, there are different bodies, so you need to find out the common point. Common point. And as you can see, between AB and BC, common point is B, right? Common point B. So what is that? Angular velocity. So in this case, you can use both relative velocity or use the method called ICZV. I'm not sure you remember that, instantaneous center of zero velocity. Since we already saw with the relative velocity, relative acceleration in here, the first problem, I'm not going to repeat that same method. Of course, you can write down that same method with the common point. You can solve like this. We can solve with this equation. I just write down here relative, so you can have the equation, find out the omega BC. So you want to common point B, so we have it VB equal to VA is 0, right? VA plus VB relative to A equal to VC for body BC, right? Plus VB relative to C. And then two equations, two unknowns in here. The one is omega BC and VC. Because you already know this is 0. This is 0. VB relative to A, you already know that is tangential to the path, in this case perpendicular to the radius AB. So you can be able to solve similar to the first problem, write X and Y components. And VC is equal to omega CD times CD, and then VB relative to C is exactly the same. On body BC, you draw the Rafa stick just like the first problem. Rafa stick. So, and it's simpler because velocity. I'm not going to review the same method that you use, that leave it to you. Go back to use the relative velocity equation in X and Y components to find out omega BC and omega CD for that two unknowns in this two scalar equation from this relative velocity equation. I use the ICZV method, instantaneous center of zero velocity. So that is another method, and it's faster, I believe, but it needs some geometry. So let's do that. So with that, we classify the motion in this case, AB, and you can see that Rafa rotate about a fixed axis, go through A. So we have Rafa, AB is Rafa. So AB, Rafa, and of course, similarly, CD rotate about D. So we have CD, also Rafa, rotation about fixed axis. And then BC, GPM, BC, general plane motion, So we have that one. So ICZV is find out the at that instant where is that body rotate about. And because the Rafa body, we already know it always rotate about a fixed point, so we don't have to do, only apply use ICZV for the body that have a GPM motion. Okay, so of course we have a 3-time motion, you already know, translation in general plane in 2D. Then we have Rafa, rotation about a fixed axis, and then general plane motion, GPM. So in this case, we just try to find out at that given instance where body BC is rotate about. So with that, in order to find out that, we need to find out 2 points on that body that we know the direction of the velocity. You don't need to know the magnitude, but only go where is the line of action, where is the line for that velocity rotate. 2 points. And normally look at the common point with the other body. Our body that we're looking at is BC. Our body like BC in here. Common point with other body. The first common point that we have, I already point out, that is body point B. And of course, the other common point is point C. And then try to find out where the direction of that velocity. So let's talk about point B. B also belongs to AB. and AB is Rafa, about 8. So the velocity always perpendicular to the radius. So as you can see, point B, the velocity have to be vertical. Have to be vertical. More specifically, in this case, it go up. It go up because it have to be same sense of direction of with the angular velocity omega AB. Omega AB counterclockwise, VB go up. So to make it more sense, right? So that we have VB. And then the second common point is C. Common point is C. And for common point C, we can have that is also belong to CD. Also belong to CD. And so also belong to CD. So C rotate about fixed axis go through D. So the velocity perpendicular to the radius. Radius here is CD. So we can be able to find out the velocity. And that it have to be perpendicular to CD. So it will be horizontal. And sometimes you don't need to know the direction. Go left or go right. In this case, you can assume direction. Assume direction. So I just assume go to the left. Of course, you can put go to the right. It doesn't matter at all. So I assume go that, BC. And that, as you can see, it's perpendicular to CD. That one here, perpendicular. So on body BC, we already know the 2 points on that body have velocity, know the directions, don't need to know the magnitude. To find out the ICZV, ICZV is the intersection of the two lines perpendicular to that velocity. So as you can see, the perpendicular line, not the direction of that velocity. So with that, as you can see, perpendicular line go through perpendicular to VB. VB is vertical, then horizontal is perpendicular line. Similarly, VC is horizontal, then the perpendicular lines will be vertical. Right? The intersection of your 2 points, that is the ICZV. That is ICZV for body BC. For body BC. The body that is have GPM motion. So with that one, we can find out the radius. So we can have that, as you can see, 4, 3, 4, 5. So that with 5 here, so that it will be 5 meters. So we can be able to find out this is 4 meters and this is 3 meters. Then we can start from what is given. In this case, the body given is the body AB, omega AB. So go to the solution. Just so I already draw that one there. Then, as you can see, start with given a body AB. Then we find out VB equal to omega R. So omega AB times AB. And that is 10 times 5. It's equal to 50 meters per second. And more specific, that one in terms of the direction, it's same sense of direction of omega AB. So it's going up. EB going up. And then we have the go to the next body, BC. Then BC it rotate about the ICZV. That ICZV that we are talking about, ICZV of body BC in there. So it equal to omega of that body. Actually, that is the one we want to find out. So omega BC. We want to find out time the radius from the point we take velocity B relative to ICZV, and that is 4 meters from B to that ICZV is 4 meters, as you can see. So from that, we can be able to find out VB already know, RB relative to ICZV already know that is the 4 meters. So we can find out omega equal to 12.5 radian per second square. And wait, clockwise.
Hey, Dr. Nguyen.
Yes.
I don't know if you're writing something you need us to see, but we can't see it.
Oh, so my internet problem. You cannot see.
I just see the diagram. I don't know if you're writing somewhere else off screen.
Can you see I move around my mouse?
Yeah, I can see the mouse, but I can't see what you're writing if you're writing something.
Did you see the link AB, link BC?
Yeah, I can see the diagram that you drew, but it sounded like you were writing equations somewhere, maybe off screen, that we couldn't see.
Oh, because I move up and down. You see that equation?
No, I just see the diagram in the question.
Oh, no, the relative equation on top?
No, I can't see that equation.
You be able to see that, right? Yes?
Can you scroll up? I can't see the equation either.
Really? Oh. Let me what's going on here? That I stop share. And my face, oh, maybe the internet, my internet have problem. I'm recording. Sorry, guys. So let's continue. Now you see the equation, the blue one. Then we can find out the omega BC. So 50 divided by 4, so 12.5 radian per second. And that one, as you can see, to try to figure it out why it's clockwise. So when we stand here, let's move to this problem. So I stand at ICZV and BC rotate about ICZV, and as you can see stand there. When you see VB going up, then the angular velocity have to be consistent. So that is omega BC, and that is the clockwise, as you can see. So that is the second problem.